Alright, so today we're looking at section 7.3, 7.4 on radical expressions. I'm going to cover these two sections together rather than splitting them up. It's very similar topics in the two sections. We're going to look at different roots like square roots and cube roots, primarily those two. And we're going to do some simplifying of roots. We're going to do some adding and subtracting and multiplying and dividing, and all of that is encompassed in these two sections together. So I'll try to cover them sort of at the same time. Now, with radical expressions, a couple things that you need to keep in mind are that radicals are exponents with fractions. We saw that in the last section, 7.2. that radicals, like square roots, are really just fractional exponents. We call them rational exponents, like 1/2. Like if you want to raise something to the 1/2 power, that's essentially a square root. And so because radicals are really just exponents, all of the exponent rules that we had way back in chapter 1 apply to radicals. Okay? And so an example might be if you wanted to, say, take a product like 2x and raise it to the third power. Well, the power distributes to the two factors, right? You end up with 2 to the third times x to the third, and you can evaluate the 2 to the third. Okay? Well, same thing is true for a root. If you wanted to take the square root of 2x, well, a root is really just a power of 1/2, and so you can treat that root just like you treat the third power. It applies to both factors individually. Okay? Now, there are times where this is very useful. Take this example. If I had the square root of 100x, and I wanted to apply that property, I could just take the square root of 100 and the square root of x, and those are multiplied together, and then the square root of 100 is nice because that's just the number 10. And so you end up with this 10 times the square root of x. So what ends up happening is the radicand, which is the stuff underneath the radical, and yes, that is the actual term. This stuff here, maybe I'll throw a different color there. This stuff underneath is called the radicand, and then this root symbol is called the radical. The radicand can be simplified. In essence, you can take a larger or more complicated radicand and make it something smaller by using this property. What's interesting is when you look at numbers, this was kind of unique because you had an x in there and it was obvious what the square root of 100 was. But let's say you wanted to look at the square root of 200. Well, 200 is kind of like 100x because 200 is 100 times 2. Okay, 200 is 100 multiplied by 2. And so it's in a similar format as this, it's just written with a number. And so if I take the square root of the 100 and the square root of the 2 separately, I'm going to end up with 10 times the square root of 2. Now these two values are the same. The square root of 200 and 10 times the square root of 2 are exactly the same value, but one obviously looks simpler than the other. Okay, because the root is smaller. Obviously just the numbers in general are smaller. Okay, and now using this concept, I can expand this to any number I want as long as there is what we call a perfect square factor, a number like 100, as a factor. Now if you think about the perfect squares, the perfect square numbers are numbers like 1, 4, 9, 16, 25, 36, 49, that's 7 squared, 8 squared is 64, 81, 100, 121, 144, and so on, right? You keep going, 169, 196, 225. And so these are the perfect squares. So as long as one of those numbers is a factor of the original number, then you can go through and simplify this, because then that factor will be able to be evaluated under the root. So let's take an example. Something like the square root of, let's see. Let's take the square root of 12. It's kind of a simple example. And instead of writing these horizontally, I'm going to work them vertically just to save a little space here. The square root of 12, well, 12 can be written as 4 times 3. And the square root of 4 is able to be simplified into a 2, right? So if I split the root up into a square root of 4, square root of 3, square root of 4 becomes 2. The square root of 3 doesn't simplify anymore. And so this 2 times the square root of 3 is the simplest form. Now the square root of 12 can be split up into other ways, right? You don't have to use just 4 and 3. You could use 2 and 6. The problem with using another combination is that 2 and 6, for instance, doesn't have a perfect square. So we're specifically looking for one of these numbers in this list as one of the factors to use. Okay, I wouldn't want to use 2 times 6 because 2 and 6 don't show up as a perfect square. Alright, let's take a look at another one. Let's look at the square root of 72. 72 has a lot of factors. Okay, and if I were to just break this down into different combinations, you got 1 and 72, which we never really consider the 1. That's 2 times 36, and 3 times 24, and 4 times something, 18, and 5 won't work, 6 will work, that's 6 times 12, and 7 won't work, 8 times 9. Okay, that should be all the factors of 72. And if you look down that list, there are several perfect squares, right? There are quite a few numbers on this list. Obviously the 1 is a perfect square. 4 is in the list. 9 is in the list. And if you go down, 36 is also in the list. Okay, so there's 4 different perfect squares. And so now you got to figure out what to choose. I'm going to choose the biggest one. Okay, we're pretty much never going to choose the 1. The biggest one is the one you'd like to choose in this case, and I'll explain why in a moment. So if I use 36, I'm going to break this 72 into 36 times 2. The square root of... Did I just write that wrong? I did. I wrote that wrong. Okay, ignore that. Should be the square root of 36 times 2. And then you break this up. Square root of 36 and the square root of 2. The square root of 36 is 6, and the square root of 2 doesn't simplify. Okay, so that works out very nicely. So the square root of 72 is 6 times the square root of 2 in its simplest form. Now you might ask, why didn't I use one of these other options? Well, let's say we used 8 and 9 for a moment. Okay, and I'll do this in another color. Let's say I used the square root of 9 times 8. Now it's always my preference to write the perfect square first. You don't have to, but I like to. And if I split this up, square root of 9, square root of 8, then the square root of 9 simplifies nicely. But what ends up happening is the square root of 8 continues to simplify. It's not in its most simple form. And that's because it also has a perfect square factor in it. namely 4. Okay, so if I wanted to split up that square root of 8, the square root of 8 itself is square root of 4 times 2, and then that square root of 4 is 2. Then you bring down your square root of 2. Now what I left behind was that 3 at each of these steps. And of course 3 times 2 is 6. So your final answer here would be 6 times the square root of 2, which happens to match up with what we had before. Okay. Alright, so that should get us a pretty good start on simplifying square roots with numbers in them.